Hi, Boone, how are you? Let's give folks a minute to settle in.
Hey guys, this is Bala.
Hey, Bala, how are you?
Yeah, I'm doing good. Thank you. How are you, David?
Good. Okay, we'll get started in a minute. Let's see. Let's give it a chance for everybody else to join, and this will also give me time to open the some of the documents that we were reviewing last time. Okay. Okay.
I, I'll be back in a minute.
Okay. There you go, Josh.
Hi, David.
Hey, Rajesh.
Hello.
Okay, so last time we did beat up a little bit, actually quite a bit on the pin group, grouping modes, all that definition. So I think that's, at least to me, it's a little bit clearer now. I did talk to Michael Durkin at JEDEC about some of these, about that, basically what we're looking to add. The discussion was in the context of TDK 1.0, where we really didn't define strongly what a mode is and grouping, what is the relation between pin groups and modes. But so just in that context, the JEP30 right now seems to have the idea that the notion of mode and just mode in general, right? I think that the focus was mostly on different functional mode and states. Like for example, they have reset called out separately and then functional. So the notion of mode is there. So adding modes, which are test-related modes, shouldn't be any problem. And then there is the notion of pin groups per mode, where in a mode you can call out pins and make them and give different attributes for those pins, right? I don't think test-related information is there in terms of properties, but the important thing is that the structure to add pin properties per mode per group is there. So for TDK 1.0, we'll just have to go over the um, different pin definitions that we had in TDK 1.0, which is basically it's the simple one, right? Clock, data in, data out. We probably will start from there and see if in TDK 2.0 we want to call we will probably want to call different attributes, but the important thing is that the basic structure is there. So integrating TDK 1.0 into JEP30 shouldn't be a problem. The other part of TDK 1.0, which is the basically extended definition of a pad, both not only in 2D and actually JEDEC has a little bit of notion of 3D, but they were treating the 3D as one composite object without being able to call out the different layers in that. So I just had a meeting with JEDEC this morning about basically enhancing that definition a little bit further so that we can call out the different the exact structure of the pad or copper pillar or bump board, whatever it is. And one thing I need to follow up is make sure we can call out sacrificial pads, which are basically going to be pads separately from other pads, right? Being able to define that, hey, here's a pad, and this pad is actually sacrificial. It's at the wafer level only, and it will never appear in the final product. Well, I take that back. It doesn't need to be bumped. Right, depending on the reason I took that back is it depends what the final product is, right? If me as a vendor of chiplets, if I decide to ship to my customer just wafers, tested wafers, that pad, the sacrificial pads may be there, so it will be up to the my customer then to bump those, the way they want it, right? So it depends on what the engagement at business level is. So yeah, right. The idea is to be able to call out sacrificial paths separately. So TDK 1.0 is moving along slowly, and it will get there into JEP30. Okay. So that's kind of my update since last time we spoke about this. Now, last time we covered the groupings and the relationship to modes, groups, and states. Maybe one thing that is left to do is from this first table to understand what is basically these three columns, right? So we can complete the first table and then we'll move on to the next tables. So Bala, if you could cover these, what do these mean? These three columns.
Okay, so this is this is the kind of events which happen. So this is the relative time with respect to these inputs or the outputs, where the the tester can stroke the values for the outputs or apply the new set of values on the input side. Right. So this is like a, so let's say if you have a different input and output delays, and and you want to do some pin margins, so for example TDO, always they do some like some binning of the signals to stagger the output delays, and then I put a yeah, deterministic delay numbers so that tester does not strobe bit early or sooner than it arrives, and have a stable value there, right?
Okay.
So
So
then
is this the is this so talking about this column?
right.
Is this the delay or is this the period?
No, this is the delay with respect to the clock period. Like after every rise edge of the TCK, like how much delay it has to wait. I just put some numbers, like random numbers, so
Okay.
we
So
can change it.
this is the delay. So if I say it like this is the delay against the clock in the signal group.
Right.
Okay. Okay.
So there is a delay for the okay. So the inputs uh, needs to have a delay, and then outputs. How do I say that?
So
There is a stroke
in
for the output.
the
It's a stroke timing.
okay. So on the input it's delay early. On the output it's delay late. Is it?
Output is a stroke. Yeah, it's a stroke window. I think we don't have to confuse a lot. Like so, we can just call a delay with against the clock. That's fine for now.
Okay. All right. Okay.
What is it?
Uh,
Why it is a NA in the title?
That's supposed to be a description, like a, yeah, I think that's a typo. I missed to put that. So you can say like it's a reference time period, might be the right title.
okay. So just for my understanding, when I hear the word period, I'm thinking the way it's a period is used in STA, right? You give it a clock, you give it a period, and within that period, you give it a waveform, right? So basically, the red period will be the repeating how often that repeats, right? In a way, it will give you the frequency. So when you and that's why I kind of wanted to understand. So, but this is not exactly a period. This is the delay,
Okay, yeah, that's
right?
right.
Okay. So you said this is a reference delay against the. Is that it?
Yeah, that's good.
Okay. Okay. All right. Uh, so Rajesh, does this make more sense to you?
Yeah, actually, what I think what Bala is pointing, or correct me if I. So whenever you are driving an AT test clock, we need to give that waveforms, the external clock waveform. I think that's when it is period as well as this uh, time it is zero, and then when the edge goes high and all that stuff that can be defined in ATPG. I think is that one you are talking about, Bala?
Okay.
Right, yeah.
Yeah, yeah. So then what scanning needs to be done, that if it is normally when you are inputting the data for the test, it need to be set up for that particular eye. So that delay should be when the data is to be ready before the clock positive edge. And for scan out, normally if it is a TC test JTAG, then if it is TDO, then it is mostly sampled at the negative edge. So then that will be after when the test
Right. So
clock
yeah.
goes
So
down,
the
how much when the negative, yeah, I think that's what. So you can put whatever the
Okay,
number.
so this is okay. So let me clarify this then. For clock, this would be the period, right? For input, this would be the
drive time.
the delay, basically it's delay how do you say it? Setup time, right? Right.
Right.
And then for output, this would be sample period.
Yeah. For to be consistent, like we can say sample time.
Okay, so the way the reason I said setup time is basically it tells you how long before the clock do we need to rise the signal so that it gets latched in.
Right.
Is it right? That's
Right.
that's basically the time setup. Okay, let me put it this way: setup delay. And then period, both on the clock, that gives you the clock period, how often it repeats, and then on the end, on the output, it is how often this is sampled, right? So you would sample it at this many megahertz, right?
So
Okay.
okay, we will sample it at that megahertz. It's understood by the waveform group. What we are saying that, and within that one single clock period, so do we have to wait for a fractional clock period of delay to for the data to be stable? So towards like they do the pin characterization, like the pin margins, like to on the tester to
Okay.
see within that period when is the data get stabilized, so that that's a stable value that I can put it in the test program, and so that they don't have to keep doing this bending of this timing across the iteration across the different wafers.
Right. Okay. So you're saying within that clock period, how much time after the how much time do you have to wait to know that the value is
Right.
stable?
Right.
Right.
Yeah.
Okay. So
Yeah.
this is the sample delay. My question is, which is the clock that I'm referencing in this case? Would that be still the input TCK, or is there a different pin that is outputting clock?
So all the tab, okay, this reset is a functional reset, right? So we would call that as a separate group. Like we just this reset will be asynchronous. So most probably this will go under like a WFT tab. Yes, it's a slow signal. There's no timing specified
Okay.
on the reset.
Okay.
So
Is
we can
this
call that. Yeah.
is it like this?
Even the reset also, like we can call it as a WFT or scan.
Which
Yes,
one is the reset?
the
Oh,
first one,
yeah.
first one. So I think the confusion is we are missing in that header row. Like I think we can add,
Yeah,
oh,
yeah, yeah, yeah,
here it
yeah,
is.
yeah.
Yeah.
Okay, okay, yeah, yeah,
Okay.
yeah, yeah. Okay, sorry, yeah. Okay, I created a whole bunch of confusion here. Okay,
Yeah, we can put that here.
I did mean to, yeah, exactly. That's what I meant.
Yeah, so what will I think what we can use that for scan in, scan out, there will be mostly the AT clock will be coming from some external test going from to the AT pin for the chiplet, and TCK will be done from a TCK source. So these are two different references.
Right. This is like a software clock generator, right? So where we need to give what's the clock period and when is the 0 is applied, when is the 1 is applied, and then there is the repeat is there, and then there is a duty cycle.
Okay, sorry guys, I'm not following you. Sorry, this is, let's see if this works a little better. Okay, so let's forget about the reset for now. Okay, forget about the reset. So we said, let me try to understand this. I apologize. I'm being a little bit. I'm just not following. So for scan out, okay, for scan in, okay, we say that we need 10 nanoseconds of time such that for scanning to settle before we can clock it, right? Only then will the value of scanning get latched into the chip, right? So basically, for the input, this is really the setup delay.
No, okay, that is not what it means. Like, so this column where we are sending, it's all specifying that which frequency group it belongs to. The next column is the one that we are actually discussing currently, like the data valid like after one like for example, a stable value of 1 is latched into the input after 1 nanosecond. That is the setup window. Like, I think your comment, I think it has to move to the next
Okay, yeah, okay.
yeah.
So really, I botched it I botched it when I didn't have that header row in here.
Right, yeah. Yeah. So yeah.
So okay. So this is okay. Let's see. No, okay. Let's go back to this. Yeah, okay. Let's start over. Yeah, okay. So this is really the period.
Right.
And then here's the waveform that says clock TCK is okay. That's giving the waveform. This is okay.
So for the waveform generator, we need to provide like a 0 at what time and 1 at what time, and then repeat at what time, right? So drive 0 at 0 ns and 1 at, let's say, maybe instead of 1 ns, let's say for 5 ns, like equal duty cycle, and then repeat at 10 ns. We can say that. That way it is like a proper square waveform. Like it is more readable.
Yes.
So
Yeah, okay. Yeah, okay. So this makes sense now. Adding the table header definitely improved this. So these two get waveforms. These four basically get
input setup time and output sample time.
So so here you have a data valid one. I'm assuming that applies to 0 as well, right? Just
right. Yeah,
sample it.
1 or 0. Yeah.
All right, just
Yeah.
Like this.
Yeah, that's perfect.
This is. Can you explain this and this?
Okay, so this is this is a repeat. Yeah,
should this be the other way around?
for the output. Yeah, I think it should be other way around. Yeah, you're right.
Actually, no. What I mean is,
For
basically, these are so okay. So
no, I made a typo. Like TX is output or RX is input.
right.
For the
So
output, we have to. Yeah, I think that is other way around.
like
Perfect.
this. Now, I have a follow-up question to this. Is
So this should also follow that data valid kind of things.
right? It's data valid at 250 picoseconds, right?
Right. Yeah.
Technically speaking, can I do like this?
Okay. Yeah.
Right. Basically, it tells me at what time the data is valid. Whether I'm
Right.
right, kind of, it implies on the input that data is valid, and on the output that I need to sample it at that time.
Yeah, makes sense. It's more readable now.
Right. So that we don't create too many different properties that cannot mean the same thing. Okay. Okay. The on the UCAE part. Okay, here. Okay, this is the period basically, and then this gives within that period where do I read or basically write the data, right? Where the data is good. Okay, the same thing for these guys. So yeah, it's the same thing. Okay. Hey, Boon, can you boot? I'm sorry. Mute your line, please. Thank you. Okay, so for UCAE, okay. Can I say this input? Basically, this needs to have two properties, right? One is that it's input, which it will have, and the other one is that this is a clock. We already have the data in. This is okay. And then date. Okay, yeah, actually, this is okay. So this last column, we'll have. We already have the data in, data out. What additional property do you need to know exactly that this is a high-speed I/O versus any regular I/O? Right, we're gonna. Right, here's what I think. Right, we by default will get for UC, we'll get which are the data pins. We'll get which are the clock pins. We'll get which are the inputs and outputs. Do you
Right.
need to call this explicitly as a high-speed I/O?
Mm, yeah, so this table, I mean to show that there is a dedicated waveform group is needed for the high-speed scenario, right? Just to avoid any
Right,
wedging of
right. So
this.
yeah, kind of right within this group, you're going to have the so you have the group, and we'll know which are input outputs. We'll know which are data, which are clock pins. Right.
Right, right,
Uh,
right.
do you need to explicitly know that this is a high-speed I/O?
I don't think there is a separate utility comes there. I'm not sure right now.
Yeah, basically, right. It's okay if you need to know that, but if it exists somewhere else where people would already kind of the test which you're running would apply high-speed I/O. Basically, what I'm trying to do is avoid a duplication of data. Right, that's why I'm asking. Right, it could be defined somewhere else in some of the other files that hey, this is already the test that is being generated would know that this is a high-speed I/O, so you cannot really use it in any other way. And in that case, providing this additional information that exists in the test here, is it valuable for the next level integrator, or is it really not valuable?
I believe the differential clock, right? That may be a valid scenario, yes, which is really on the very high speed and a dedicated routing channel.
Okay, but okay,
Right.
so but that
For
would
the high
fall,
speed clock, yeah.
that would fall into the SI kit. In the SI kit, what we want to do is take a group of pins and say, hey, this group of pins is a UCA interface. And within that UCA interface, pin C plus is clock and pin C minus is clock, right? And then pin D is data and so on, right? Whichever way the vendor has named their pins, right? We can then go and identify, right, with the actual names. These are the pins from that. These pin names are actually the pins from the UCE standard, right? So kind of do
Right,
that
right,
mapping. So we will
right.
know that hey, here's the pins, and these pins are UCE, and that UCE is running at gazillion gigabits.
Right, right. So signal integrity and even the AC parametric test, like if they want to do like check this trimming kind of things, right? Where the
Yes.
training sequences that might also care about which is the positive and which is the negative node of that differentials, right? Each pin has a positive and a negative
Okay.
nodes.
Okay. Yes. We can define that. That's going to be in the part of the UCE mapping, right? Where we take
Right,
the
right.
UCE standard and we map it onto actual pins, and we say these pins are each pins on this chiplet maps to that pin within the standard. So that information is there, and we will kind of that would imply that this is already we know okay, this is whether it's UCE, whether it's SerDes, whether it's DDR interface, right? A tool, in my opinion, should be able to know, right? Especially when we're talking about standards, right? Hey, here's the standard,
Right, right.
and should already be able to know exactly what they want to do with that.
Right, right.
Okay.
Yeah, so I can dig through that the VSTL, like the VSTL, there's an exact application is specified. Maybe we can refer that also to see what attributes that they really care for those tests, right? The AC tests.
Okay, if this is defined in the BSDL, that is going to come with the chiplet, or somebody will generate, then there's no point in actually, let me put it this way. Let me ask you a question. Would a vendor give you BSDL or something? Right, when a vendor gives you chiplet, do they also give you their BSDL, or you get the chiplet and then you have to define the BSDL?
Okay, so the vendor, they will give the BSDL for the wafer test, but when it goes to the package, right, the SIP guys, they decide based on which pins are going outside the to the package. So that's where the SIP level BSDL finally define the exact IOs which will go outside of the package, and that will be exposed for the final test, right? So there are two different BSDLs are getting involved here,
Yes. Oh, yeah. Okay, got it.
right?
So for that,
But then the BSDL will also say that the positive and the negative polarity of those same ports, and it will say that which will have that exact the pin name suffixed with the P or suffixed with the N. So
yes.
that way there is a pin naming rules applied there. So that I believe that may be okay for the boundary scan kind of test, but this here what we are talking about is even for the interconnect die-to-die ATPG tests. Also, like so, there are care about when they are interfacing this. Uh, I mean, for the die-to-die test, it goes inside, so I believe it doesn't matter for the ATE operations. Yeah, I think we can leave it like that. Like we don't have to go very detail on that. Like it's just given this table, it gives users like a yeah, different groups of signal groups, right? Based on the GPU or scan or JTAG or the high speed IOs. I don't think that we need to. It maybe just the UCE clock we can add it. It's a differential clock.
Yeah. Yeah, that will come. Okay, let's do that. Let's add the UC clock as well, just as a good example. This is not a pair, right? And let's say TX CKN, right? We are saying these are outputs. They are within this group. This is the period. This is the clock, and this is the
If you comment, we can add it. It's a differential pair.
right. But these already these should be part of these would be this actually this will be part of SI kit, right? Which is going to tell us at least from what kind, right? That it will specifically identify interface and would imply high speedish interface, right? Depending on its mode. Okay. Do you agree with this? That we don't, basically what I'm saying is we really don't have to call out, right? We have the group, we have the directions, and we really don't have to call out these as part of the test mode. We don't have to call them out as being high speed versus GPIO, because the SI kit will already identify these as being part of a high speed interface. And within that high speed interface definition, it will identify input, output, clock, positive clock, negative clock, and so on.
Okay, that's fine. Yeah.
Right?
So,
okay.
Yeah. So, is there any specific attributes comes there in the SI kit, like whether it's a GPU or high speed? How that is going to help you?
So we are still working through that part of the SI kit, right? Our right now where we are is basically looking at the electricals, but the mapping to the standard to a given high-speed standard is kind of next thing that we're going to work on. Is there any specific property you're looking from that, or
Yeah, I mean, for the signal integrity, like there are multiple things are involved, right? And the different modelings are involved. The noise, jitter. So it's not
yes,
just
yes,
the like a digital signaling kind of thing. It's more analog centric. So
yes,
that's
yes,
where
yes, yes,
I'm asking.
yes,
Then once we get into that, like there are more discussions which will be called for. Yes,
yes.
I'm not SAP expert, maybe
Yeah. Here's what
the
we're looking, right? Well,
Mhm,
here's a preview of what we're looking at from the SI kit, right? We're looking at whether it's a serial or parallel, the data rate is running at, what kind of data encoding, which are the data pins, then the clocking scheme. There's many different ways to clock this, which are the clock
mhm,
pins. Then we're looking at data skew with regards to clock. Then word and byte skew, data actually sorry, there's data bit skews within the between bits. Then there's with regards to clock, clock timing mismatch, clock jitter, and then here we start talking about impedances, capacitances, I shape, width and height limits, equalization, slew rates, receiver impedance, voltages, overshoot, undershoot, even jitter is added again.
mhm, mhm,
Link with modulation band. This is actually for optical, yeah. And then maybe specify under what PVT we are talking about.
mhm.
Right.
Yeah, I think
So,
yeah, TDK, which involves more um, like a design specific involvement than our what we are scoping for the test.
right.
Right? So test is mostly like a scan, like a test vector versus the ATE operations, like how that translation and applying on the tester, right, in the tester software, right? Those type of things are mostly digital. So
Right.
here it involves more of a inter-tool operability related to analog. Um,
Yes, right. Yeah, I would expect basically either the test insertion tool or whoever's generating the test to basically specifically for high-speed interfaces to kind of use the information that's provided by the SI kit
uh-huh.
to
Mhm.
understand what is it that they need to do. Obviously, right? If you're inserting vectors, uh, I mean the vectors for the test vectors for high-speed I/O. I'm guessing, for example, they really wouldn't care about um, implementation specific targets, right? Which is basically eye shape and eye width and height limits and things like that, right? The test insertion flow should probably assume that these targets have been met or they will be met, but probably you care about which are the clocks and maybe data encoding if you want to, if it supports different modes to encode it, or different speeds. What does it mean to run the interface at different speeds, right?
Mhm.
Okay. So, okay. So I'll leave these basically not specifically call out high speed versus GPIO as part of the TDK, and we'll reuse the SI kit information.
Mhm.
Okay, good. So congratulations, guys. We finished the first table. um, Now let's do the next one. Okay. let's see. Okay. Oh shoot. Oops. Excuse me. What I want to do is okay. Okay. Walk me through this table. What's the intent here?
Okay, so this is for the different characterization test requirements, right? So right now, so when we are doing this characterization, like there are different temperature testing. Like there is a hot temperature, and then there is room temperature, and then there is a cold, right? So each wafer defines a specific plus or minus 3 delta, like 3 sigma variants, and so which are optimized for the time in one scenario. The other is optimized for the setup, like so performance versus stability kind of scenarios, right? So here. Um, in terms of this thermal workflows, right, we get a readout of what is the max capability across the pads, like what temperature it's characterized, and those from the pre-silicon standpoint, right? So those database will have a readout of temperatures, right? So this will give yeah, um, a yes, spec directly extracted from the database, and so that it kind of goes as an insurance for the ATE testing, yeah, for ATE test program development, right? So sometimes yeah, junior guys comes in and tries to operate it, and they try to change the temperature for hot temperature for one device like 125, and another device may be like 110, right? So sometimes they kind of arbitrarily choose it like by mistake without referring the data sheet or the documentation or the request comes from the customers, right? So that could be a mistake and it can burn out the chips in those scenarios, right? But having this interoperability, extracting those database like a thermal workflow space test database, which will give yeah, you know, what's the minimum temperature and the maximum temperature window for any temperature based testing on the ATE,
Okay.
right?
So
So
let me understand a couple of things about this. Is this how is this data generated? And when? And kind of by when I kind of mean more like where, in the sense that I'm developing the chiplet, right? And the chiplet is my product. So for my own wafer testing, I would need to do this, right?
for
Or no?
wafer test, I don't think a hot temperature. I don't know if there is a hot temperature that they do. Like, because that might
Okay.
burn out the wafers or might cause
Okay.
some damage for the because it is not because the does not have that or the your thermal shielding which is comes after the during the package, right?
So
So
is
uh,
this meant to be
for
for
the
final
final
test?
test, right?
This is okay. This is final test related stuff.
Right.
Uh,
So the question for the users, right? So how do they make sure that they don't cross the temperature boundaries what the device supports it, right? So that spec currently it is exchanged through a data sheet.
Yeah. Okay. So
So this may be a good question to ask thermal work groups, like if there is any people in the OCP side, like we can ask them like at what point of time you will know that this thermal like what's the pre-silicon characterization result of the pads or the pad boundaries, right, on the NV. So in this applicable all the way through the analog pads and then the hybrid bonds, microbumps, right? So all those integrations, like what type of thermal database that they have when it is available for the ATE for the integration.
yeah, so
And also
okay,
the
so
derating factor.
when you talk about pads here, are you talking about the pads on the package, or are you talking about the pads on the chips?
Both actually, because the pad cells like on the within the chiplets, right? So the IO cells, like what people are adding it gives um yeah, it's an analog cell and also it's a bigger cell, like so that's the one that they will be using it for strobing for any debug also, right?
Okay, so let me okay, so the chiplet, whoever I bought the chiplet from,
Mm.
what do they need to tell me about their chiplet? Is any of this information something that they have to tell me?
Um, yeah, I would say it should be there as part of their it will be there as part of the data sheet of the IO cells from the chiplet standpoint.
Okay, so this will be something that the uh, um, this table here is going to be a piece of information that whoever did the chiplet, they would have to characterize or simulate, or one way or the other generate this data and put it in the chiplet data sheet, so
Right.
that when I'm integrating two chiplets together, I can use this data. Is that is my understanding correct?
Yes, that's right.
Okay.
So let's say if you start with the last column, right, the timing margins, that is easier to discuss, right? So any prime time or any timing database will have this information, like where for the clock they will have the clock period, and then what is the um, uncertainty window that they have budgeted it, and then similarly for the reset when it is safe to assert it and deassert it, and the scan any GPOs like scan in and scan out and JTAG. There is a setup and hold and is already there. And for the high speed IO, there's the I margin and the jitter and the bit error rate. Those type of information are the crucial informations which will be really useful for the for the SIP level integration teams, right? So that they can adjust the timings for the integration, like for the interconnect delays, all those things. When they check it, so these timing models will be really useful. Like this is a start
Okay.
point for them for the any top level like a SIP level timing closer.
Okay.
And the
What
same
is
thing it goes here. Mhm.
how do you use the temperature derating? What does this mean?
Um, so this one, let me think loudly. So, so this is like a, you can call it as like a variations, right? So temperature, it's it's not a fixed temperature always. Like it goes ups and down, it moves. So there will be some variation there. So there's a guard band which is internally applied, like where you can say when it is derated, like those cases, if it is elongated exposure of the hot temperature, let's say, or it goes ups and down. Like so, there is a derating budget that they apply it as a guard band. So it's like
Okay.
a
Yes.
uncertainty window, like for the clock period, right? For the 80 clocks when they define the clock period, and then they also say some uncertainty. So that's a derating factor. Like so it will be like a plus or minus of like 15% from this clock from this particular temperature, or plus or minus 10% as a guard band, right? Beyond that, the it might cause damage to the device, or it might the operations may be not guaranteed kind of scenario.
Yeah. Okay. Okay. I think okay. So this is basically a piece of information that the timing tools will consider when doing the when doing STA or something like that. Is it?
Right, right.
Okay. This
And
is how many.
this is how many cycles that you can expose such an operation, right? So, for example, uh, with the ATPG test, when they do this burn-in kind of test, they put the device in the hot oven and then run it for couple of days, like for to determine the aging factor. And some of these pre-silicon tests also it can give that signaling of the aging problems, and we also we do not want to elongate. Like, yes, today there is no hard and fast rule where you can put this device in this aging test condition for these many days, right? It's just that incremental trial and error kind of method. They try to stretch the goal and then see whether the test comes back alive, right? And so they will post test it in a normal room temperature or cold temperature to double check whether a portion of the device is alive or completely alive or completely is dead.
Okay.
Right. So
Okay.
and then based on that, like how much you extend the hours. So based on that, there is a model that they say that okay, in the real time, so it can this particular device is guaranteed to work for at least 4 years or 6 years, something like
Yeah.
that. So this
Yeah.
is
Okay.
yeah, giving that data from the burden kind of test calculation results.
Okay.
So the
Okay.
so
And then and
this
then so
information. Yeah, this information will be readily available from the pre-silicon calculation also, right? Where the spice simulation guys, they would know that in their pre-silicon reliability test, when they do this type of aging kind of um simulations with their modeling, like
mhm,
how they model it, and they can give some theoretical window of this make cycles.
yeah. Uh, do you expect this information to be provided for every pin, or it could be provided for a group of pins? I mean, a group of pins, I mean this group of pins.
Right, right. Yeah, or each
Or
group of,
would it
yeah.
be, or would it be uh, per mold, or would it be for the entire chip? Basically, I'll come in and say, you know what, for the entire chip, apply this much margin.
Um, Yeah, I don't know if there is a straightforward method. Like, yes, I'm not an expert on this, like on the stress test. But I would say like mostly it is again depends on like what is the load internally, right? So for example, TCK, it goes everywhere in the chip. right? And the scan in and scan out does not go everywhere. It just goes and meets at the first flip-flop or wherever it meets the first mux, right? So the load is not so high on the scan in and scan out compared to the TCK, right? So I would say the critical paths, the timing critical paths, and then the load, the quantum of the load and the particular pins, right? That those factors give more weightage um, for the early failures in terms of the stress.
Okay.
And again, silicon results might use some other inputs also, right? Based on what type of pads and micropumps,
Yeah. Yeah.
copper bonding, like so. Yeah, there are a number of material aspects on that. But so this is all I want to highlight it because most of these informations today it is exchanged through the data sheets and the emails, and so the all those workflows has to come together to automate this process.
Okay. Yeah. But so it is exchanged. Yeah, we want to digitize that, but does the exchange happen only internally within the chip developer, or it happens between the chip, basically the chiplet developer and the chiplet integrator?
Yeah, this is made if the useful data for the chiplet integrator and the ATE unit test program integrators.
Okay.
And yes, those integration peoples are the benefiter of this data.
Okay, I understand. Okay, yeah, that's good to know. In that case, right, the reason I'm asking that, I wanted to understand whether this kind of crosses boundaries where we need to provide this information, right?
Right.
Right. Okay. Cool.
And which are also in real scenario, like these type of corner cases comes really in the late game, right? So it
Yes.
calls
Yeah.
for some of these areas causes for like most critical ECUs, like physical
Yeah.
ECUs. Like,
Yeah. Okay. Good. So, folks, we're at the actually a little bit past the top of the hour. I'd say we continue next time with the next table. Here, we covered this one table. Are there any questions from anybody? Rajesh, Boone, any comments about this? It looks fairly straightforward. Is it? Anything missing?
No comments from me. That's good.
Okay, good. Okay, then we'll resume again in 2 weeks and we'll tackle the next table. Next week is SIP kit. Test design kit is in 2 weeks. So I'll see you all next time.
okay, sounds good. Okay,
Okay.
thank you,
Right.
guys.
Thank you.
Thanks everyone.
Bye.
Yep. Have a good one. Bye.
Bye.